Thank you very much. I would like to thank Professor Mark Steif for inviting me here. I would also like to thank Mia Feder, who asked me at first and has been a perfect host so far, and I'm still hoping for even more. And I would like to also thank Irit Neuländer, who organized everything so perfectly. Now, from my room, I can see the beach. Now, we don't have a beach in Lausanne. I come from Lausanne. We just have a lake. Okay, so that's the best we can do. This is like a shot, like a 360-degree shot, and there's actually a camera. If you look down there, you can look at any point in time. Right now, it's going to snow, okay? If you want to see some snow, just go to the camera, and you can see a little bit some snow. Now, I've been working, mostly actually on coding, and that's exactly what I would like to talk to you about. And if you think a little bit about the history of coding, which started exactly with Shannon's 1948 paper, then I guess naively I always thought of the history of something, fairly linear, people steadily coming up with some great new ideas, new products being developed, etc. But if you have a little bit some time and in the evening and you don't want to watch any more YouTube videos, okay, then I can recommend this one here. You can find it somewhere on the web. It's like a talk by Jim Massey, and he describes history in a slightly different way. And if you think about it, it actually makes perfect sense. It's a much more cyclical history in which he describes actually how coding, and I think this applies to probably many areas in science, really since its inception has gone through many cycles. Cycles in which there were bursts of development, excitement, and then cycles in which people said, has all been done, nothing interesting to be done, it's dead, okay. And there was essentially a big depression, and he describes whole workshops in which the mood was essentially, collective suicide, jumping off a cliff because everyone thought there was just nothing interesting to be done anymore. Now, I don't want to go through this whole thing, but I want to, just give you, just the gist of it. And again, this is not, of course, a complete history of coding. Would be ridiculous in one page. So there are many, many interesting things left off. But essentially, the phases he describes and the four kind of phases and depths that he's described that we have gone through are first, very initially, the first paper was actually not by Hamming, but was actually a paper by Gola in which, this was not just a paper in channel coding, but also a paper in source coding and compression, because in one page, if you look at how much content there is to one page, and I guess if we compare this these days to how much content there is in average in one page, it's just amazing, okay, and embarrassing and humiliating, I guess. But this was kind of the first paper, and there, all the kind of classical codes, Reed-Solomon codes, BCH codes, convolutional codes, they were all, done in fairly short succession, but people didn't really think that this was of much practical use. There wasn't, it was kind of nice, intellectually pleasing, but it was not that people thought that anything, that this would be in products, that would play a big role. And so essentially after that, people were discouraged, mostly happened at MIT, many things happened at MIT, not everything, but people were discouraged to even continue on these kind of topics because they said, well, essentially we know everything that can be done on this thing. It's nice, intellectual, but it's not of much practical use. Then there was this second spurt. So this actually happened mostly at MIT, was LDBC codes, massive threshold decoding, concatenated codes. And then there was the first real application, which was actually meant to be a backup for another system, which was one on a probe, and then it worked out very well. And so after that, again, there was lots of excitement. There was even a company that got founded out of these three thing codecs, which later on was bought by Motorola. And there was the first application, but still, afterwards, the mood was essentially, well, it's very nice. Everything that we know, and anything that possibly could be said about coding has been done now. But it's not of much practical use except maybe for space explorations, etc. And then we get to the third phase, which was the Viterbi algorithm and the interpretation by Forney about the Viterbi algorithm in terms of a trellis, which again brought a lot of excitement. But even at that point, at least according to Jim Massey, the thought was that, okay, coding is not really that important, not really that interesting for practical applications, except if you have essentially infinite bandwidth. And again, it was essentially a death, and he credits then really Ungerberg with his invention of what's called trellis-coded modulation, that he was kind of the first one to, when he showed that you can use this also for channels that have, in a practically and usable way for channels that have bandwidth limitations, that really he, essentially introduced that and really made this something that people thought of now of being practically usable and being of value in an actual product. And again, after that, he claims that essentially people said, well, you can play around now with the exact, the modulation schemes and exactly how you do the mapping. But people again thought that there wasn't really much else you could add. And then, of course, much more recently, about, now it's already 16 years ago, there was the introduction of what was called turbo codes, or also the reinvention of or rediscovery of these LDDC codes, many other names that describe this as codes on graph, iterative decoding, message passing decoding, modern coding theory, whatever you give it as a name. And there, this was clearly a huge leap forward. And at that point, when Jim was giving this talk, which was 2001, he basically said, well, let's give it another 3-4 years. At that point, we'll have more or less figured out how turbo codes work. And at that point, it will be, again, all dead. Anything that there is to say about coding will have been done. And, what else could we possibly do on top of it? Because these codes, after all, are, fairly good. They have fairly low complexity, get you, quite close, at least for relatively large lengths, to capacity. What else could there possibly be done there? Now, of course, we know that, this is certainly not true. And any time you predict, that the demise of some area, you'll be most likely proven wrong. Just to mention 2 other things that have happened since network coding, which has spurned a huge area and in itself has become a very, very nice topic and very promising topic, rateless codes, and many, many, many other things and I apologize, there are many things that I have left out here. So what I would like to tell you now is one more story, something that's even more recent, something that goes back to Erdal Arikan, and which is called polar codes. And it's, I think, a very, very nice story, and I would like to just tell you a little bit what this story is. I know that there are many super experts in this room, but I also know that some of the audience is more mixed, so I'll start more or less from the beginning, and I apologize to all of you that, of course, know this story very well. And I would like to tell you a little bit what this story is. I would like to maybe convey a little bit some of the enthusiasm, why, many people think that this is something very nice, very elegant, somehow exciting, something very much in the spirit of Shannon's original work, and then maybe try to give a little bit my sense of where this thing might be going. Okay, so just to give you a few points, as I said, about 2 years ago, Erdal came up with this idea. It's a very general phenomenon. So this phenomena of what he calls polarization, once you think about it, it's essentially a phenomenon that's impossible actually to avoid, even if you wanted to. So it's not something that you have to actually work very hard to get, but it's something that you would have to work very hard not to get. And so to some degree, it's actually surprising that people haven't really made use of this before. It's somewhere in terms of coding, it's somewhere between the classical code. You will see some connections to very classical things like Reed-Muller codes, and something that's closer to maybe this message passing decoding, but has a very distinct information theoretic flavor. And that's, I think, why many people get excited about, even if they're not originally, let's say, in coding. And this is maybe somewhat a fluffy statement. It's a scheme that's proven to achieve capacity and do many, many other things as well. And it has very low complexity. But what exactly that means is quite tricky, because we're talking not about now things like polynomial versus non-polynomial, but we're talking about constants in front of some linear time algorithm or almost linear time algorithm. And so then it's much harder to determine what exactly we mean with complexity. There are many variations of the theme. I'll tell you a little bit later on. And as I said, this is not just good for standard coding. You can use this for source compression. You can use this for multi-access channels. People have looked at many, many papers, and I think there will be many, many more. And so far, pretty much anything that people have looked at, it works. Some time ago, I think it was Uri Aris and Ramzamir who wrote a paper saying lattice codes which are good for almost everything. Okay, so this is the equivalent. Okay, polar codes are, I guess they said lattice codes which are good for almost everything except for making coffee. Okay, I think the same thing applies here. Okay, good. Now, if you're interested and later on want to go, if you just look at, for example, arXiv, this is fairly recent, so not many papers are actually published. This is roughly what you see, so it's still manageable. But I think you can kind of see already that there will be many, many other things written. There's still, I think, lots of nice open problems and still some low-hanging fruit. So, it's not all done and said yet. Okay, so since I know that this is a somewhat broader audience, let me just for 2 minutes just make sure that we all know what we are talking about. So we're talking about coding. And so what we mean with this is that we want to convey some information, either from here to some other place or from a certain point in time to some other point in time. And so by doing this is we choose some information, and let me call this information, let's say, X, and we choose this from a certain set of messages that we possibly want to send, and we send this over a channel. Like sometimes channel models that I will talk about will be something simple, like the binary ratio channel, where bits are simply being erased or not, binary symmetric channel where bits are flipped, or Gaussian channels where you add additive Gaussian noise to it, and you send this. The channel itself will somehow introduce some noise to it, and of course the aim is that you want to recover from the observation why you want to recover what this is. And so in particular what we're sending are typically what I'm going to talk about. I'm going to talk about the binary case. All what I'm sending are bits. And I'm going to talk about the block coding case. So I'm talking about that these messages that I'm sending all have a particular length, and I'm going to call it capital N. And I'll choose one of these messages here. And of course, all the things, the examples will give up Tor examples. If I wanted to send, for example, 1,000 bits, then of course the number of such messages would be 2 to the 1,000. But of course, I'm going to talk about some small things. So where here I send essentially 2 bits by choosing one of these 4 messages that I want to have. Okay, now in order also even more concretely, in order that we can do this in an efficient manner, we need to get some structure into this code. We don't just want to choose n tuples out of all the possible n tuples in some arbitrary nonlinear way. But typically we do this in a linear way, and for many channels that's known to be good enough. And the standard way of doing this is by generating the code via what's called a generator matrix. So thinking of the code as the row space of such a matrix. And what I mean with this is that I pick a matrix. The length of it is the length of the code word, and what's called the dimension. So the height of the matrix is the dimension, and the dimension is related to the number of code words. That if I have k is 4, then I have 2 to the k, so meaning 16 code words. So all possible linear combinations are the code words that I want to send. And so I have basically the relationship between the actual information that I want to send, which is a k tuple here, which I hit with the matrix G, and what I get out is the code word. So just to be completely explicit, for example, if I want to send these 4 bits, 0, 1, 1, 0, then I would multiply this with the matrix G, and this corresponds, since I have 2 1s here, then taking the linear combination of these, or the sum of these 2 rows here, and that would be the code word. Okay, so all I'm going to talk about will be exactly this framework: binary, linear codes, and some very simple channel models. Okay, now let's go to try to define what these polar codes are. Now, the starting point will be something very simple. I'm going to start with this very simple matrix. Everything is binary here. So 1, 0, 1, 1. And what I'm going to do is I'm going to take the Kronecker product of this. So what this means is whenever I see a 1 here, I'm going to replace this 1 with the matrix itself. So I have here the pattern 1, 0, 1, 1. But now I'm going to replace the 1 with the matrix itself, matrix itself. And now I can expand this. Okay, so this, remember, was originally the 1 here. And now this is replaced by 1, 0, 1, 1. And whenever there was a 0, this is replaced by the 2 by 2 matrix here. And now, of course, the matrix went from a 2 by 2 to a 4 by 4 matrix. And so I can do this again. I can again replace the 1 here with the original matrix G2. And so every time I do this, I will double the size of the matrix. So let me just do this one more time here again and expand out. So now I have an 8 by 8 matrix here. And so in general, if I do this n times, what I will see is that the length here, so remember I will later think of this as the generator matrix, and we'll have to discuss how. The length here will be 2 to the number of steps that I have taken. M is just the number of steps here. And so this will build the generator matrix for some code. Okay, so we're thinking of this as the generator matrix of a code. Now, remember, this is the relationship. This will be the information that I want to send, and this will be my code word. And there will be also a graphical representation of this. So this is simple, a graphical representation of this matrix product here. In what sense? Well, let's look, for example, at the bottom row here. So if I just look at the last column here, so the last column here, if I multiply this with this vector here, all it does, it picks out U7, right? So we see that X7, the last element here, is simply U7, right? So that's simply the path that goes straight through here. Let's look at a slightly more complicated one. So for example, what is how do I get x6? So what's the graphical representation of x6? Well, you see that this corresponds to multiplying this column here with the vector here. And what does this column do? It simply takes the sum of the last two elements here, u6 and u7, and that's exactly a representation of it. You take the path from u7, you add it to u6, and you have a path to x7, x6, right? So I hope that you see that these are simply paths that go from left to right, and whenever, like here, it splits up, this will be added, there's some other added here. So this is simply exactly the matrix product that we have, and this will play an important role. And just to let you know, this length here will be n, and somehow the number of layers you can see of kind of the layers that you have here, this will be of size log n. So the kind of whole grid is something that is n times log n. And also, if you, of course, know a Fourier transform or fast Fourier transform has a structure very similar to this, and this will play an important role because you will be able to do algorithms that have complexity n log n, very similar as you do algorithms when you do the fast Fourier transform. Okay, now, this itself is not very interesting. Why? Because this is a square matrix, right? This is a square matrix of full rank. So if I'm simply multiplying a vector here of length 8 here with this g2 to the the third power here, all I'm doing is I'm transforming, right? This is not really a code. I will still get all possible vectors out. There's simply a mapping between all the vectors of gf2 to the 8 and gf2 to the 8, but it's not really a code. So how can we make a code out of this? Well, one way to make a code out of this is by simply scratching some of these things, or another way is by retaining some. So for example, let's assume I just retain these rows here and I scratch the rest, right? So there are two ways I could denote it. I could either simply delete them and write down a new matrix, or what I can do is whenever I want to delete a whole row here, what I can do is I can simply put a 0 here at this position. That's the same thing, okay? So what I'm saying is that now I have a relationship between x and u, but u has this funny structure in that the component 0, 1, 2, and 4 are permanently set to 0, right? So now I have a mapping from a 4-dimensional space to an 8-dimensional space. So now I have a code of rate 1/2. I expand the vector really by a factor 2. But why is this nicer? Well, why do I want to do this? It's nicer to keep this whole structure. And what does this correspond now in the structure? All it corresponds to that I have now permanently set this to 0. And so if I set this to 0, this will not add anything. So I can simply think of some of these things being deleted, some of these lines. But another way is to simply think of that some of these points are set permanently to 0, and I keep the whole structure. And it will just be nicer to keep the structure and set it to 0. Okay, so now the question is, of course, what rows should we pick? Okay, what would make a good code, and why should I pick this? And people have thought about this for a long time. Actually, in about the 50s, this was like the first column that I had, the first set of papers that I had up here. Rüdiger and Müller thought about a way to do this. And they thought about the following. They said, well, let's try to pick those rows that have the highest number of 1s. So you can see there's, for example, this row that has only 1 1 here. This here has 4, this has 4, and this has 8. So let's try to keep, given that I want to keep a certain number of rows, let's try to keep those rows that have the highest weight. And why did they decide on this rule? Well, it turns out that what in general, the classical view of coding, what's good to have in coding is to have the code words, if you think about them in what's called Hamming space, to have the code words as far apart as possible. And as far apart means that if you think of them as vectors here, that if you take what's called the Hamming distance, so you simply look at the corresponding components, and then whenever one is 1 and the other one is 0, you say there's a distance 1, and you add over all the components you have, and you would like to have this distance to be as large as possible. Now, this code is, so what you should do is you should look at all the code words you have, you should look at all the pairs, and you should make the Hamming distance as large as possible. So that's the classical view of coding. Now, since it's a linear code, trying to maximize this difference here is the same as maximizing the weight of all the non-zero code words. That's the linearity of the code that does. So what you should do is you should write down all the code words except the 0, 1, and you should look at what weight they have, and you should maximize the minimum weight. That's the equivalent rule. Now, in general, it's difficult if I give you a generator matrix and I just tell you the rows. There's no simple rule to deduct from the weight of the rows to the weight of all the possible linear combinations. But this is a very special matrix, and it turns out that whatever weight you have in here, the lowest weight you have in the rows, that's indeed the weight of the code here. Okay, that's very special. So it just turns out. So for example, this code, if you pick these rows here, this code would have minimum distance 4 here. Okay, and that was the rule that Reed and Müller indeed did. And these are codes these are nice codes. Have not really been used that much in practice, but these are nice codes and probably have some very nice properties. But this is of course not exactly what polar codes do. Polar codes are very similar, but there is one big distinction. And so this is now one of the key slides trying me to convey what polar coding really does. So here's again this matrix product here. Some of, this is, you think of that you put here some information in here. This information will give me the code word that I have X. And now these bits are sent through some particular channel. Okay, so some channel W, and this will be the observation. The question is now, which of these bits should I set permanently to 0, and which of these bits should I actually use to convey information? And so the rule that Erdős came up with has to do with successive decoding. So let me try to explain what successive decoding here is. So Erdős said the following. Well, let's try to only figure out what the bit U1 was. Okay, so let's try, we were only interested in this. And let's assume at decoder, I would have no idea what these other bits are. Okay, all these bits I consider to be simply noise. Okay, I have no idea what these bits are. And all I'm interested in is to decoding the bit U0 here. But what I do know is that the decoder, I know this whole vector here, y0 up to y7, okay, these 8 observations. Well, I can think of this as a channel. So I have U0 as an input, I have the observation out here, and I think simply of this as a noise. Well, this is some channel, has some capacity, has some error probability if I did optimum detection. Okay, fine. Now, let's assume that we succeeded from the vector y to actually figure out what the U0 was. Okay? And just also as a word of caution, I'm doing everything here with length 8, but in reality, this should be 1,000, 10,000, 100,000, a million. Okay? But I'm just doing things here of size 8. Well, let's assume we succeeded. Then what I could do is I could now try to be more ambitious and try to figure out what U1 was. But now, since I already know U0, I can think of a channel that has input U1 and has as an output, what I'm given is the whole observation y plus also the U0. Okay, in addition. So I have some more information to detect now U1. So again, this will simply be a channel. This will have a certain capacity. And so now I hope you see what the game is. Every time I assume that everything in the past is known, and that everything in the future, everything down, is completely unknown to me with uniform distribution. So I have a channel U2, I have a channel for U3, etc. Okay? And so these channels are done by what's called successive decoding. We successively decode one bit at a time. So what I've succeeded now, making out of this matrix here, 8 different channels, 8 channels. And so now, what we would like to do is to consider using these 8 channels for actually transmission of information. Okay, now here is where the magic starts, and this is really why people got excited. Now think of this, that this becomes large, not 8, but this becomes 1,000, 10,000, a million, a billion. Okay, this is a large set, and you do this over and over again. So the block length becomes large. Now what happens is that these channels are not just any channels, okay? But these channels can only be one of 2 types. Either such a channel will become completely noise-free, okay? Will become a perfect channel. You simply put a bit in, the bit comes out. Or this channel will become completely useless, okay? You put a bit in, and with, even under optimum detection, your error probability will be 1/2. Okay, so it's only one of these 2 types. Okay, so that's already this is exactly what he called polarization. And now what happens, and what's now particularly interesting, is that how many of these channels will become good and how many will become bad? Well, if none of the channels becomes good, that's not a very useful scheme. Well, the amazing thing is that the fraction of channels that become good is exactly the capacity of the original underlying channel. So let's assume you had a channel, it's a binary channel, has a capacity between 0 and 1/2. Let's assume the channel had capacity 0 and 1, the capacity was 1/2. Then exactly 50% of these channels, when n becomes large, will actually become these perfect channels, right? And so now it's very clear what you should be doing. What you should be doing is that the useless channels, the ones that become completely useless, there's no reason to use them at all. You will simply set them permanently. Okay, you figured this out beforehand. And if you decided that U1 was a useless channel, simply permanently fix this to 0 and beforehand agree with the decoder that this channel is useless and its output is always 0. Okay? So what you do is you simply decide on a set of good channels and you decide on a set of bad channels. So let's assume these are the bad channels here. Let's assume these were the good channels. These you permanently set to 0. And you agree with the decoder that beforehand that these bits are all permanently set to 0. And these are exactly the bits, these will be the good channels, which have essentially 0 error probability. That's where you will send the information. Okay, so that's what polarization means, and that's what actually happens. Okay, so let me just maybe give another demonstration of this thing. So this is again the picture. We decided, let's say, that the bad channels are 0, 1, 2, 4. F stands for frozen. We permanently freeze these things. And so now the information is now on bits 3, 5, 6, and 7. And so now I fill this information with some bits here. I get a code word out. The rest here is 0. I get an observation. And now I'm doing this successive decoding. But anytime I get a bit which is permanently frozen, I don't need to actually do decoding because I know already what the output is. So I go from 0 to n. And every time I discover something, I try to decode a bit that's already frozen. I don't need to do anything. And every time I see a U3 here, then I know already that these all were 0 in my channel definition here, and I simply decode now the bit at optimal manner. And it's not so maybe obvious right now from the structure, but it turns out that you can do for every time here what you can do the decoding with a complexity n log n. Okay, so the number of operations is fairly small, and you can do this very efficiently. Okay, now maybe this is just another picture of it. This is now for length 16. I have decided, I've once computed the quality of these channels. These numbers, 1 means completely useless, 0 means very good. These are the frozen kinds. This is where I have the information. I set this information to something. I get a code word out. This is for an additive white Gaussian noise channel, so my modulation is plus minus 1. I send this over the channel. Okay, so these are my likelihoods here, or log likelihoods here. And then I simply do the decoding exactly in the fashion I do. And these are the likelihoods here. And if it's positive, and if it's larger than 1, it will be mapped to 0. If it's smaller than 1, it will map to 1. Okay? Good. Now, let me just try to show you now how this polarization goes on. I'll tell you in a second why this polarization happens. But let me just visualize now how this polarization happens. So this is a channel with 4 elements. And what this shows you is the channel quality. Okay, so this shows you the error probability of the individual channels. There are only 4 channels that I have. And, okay, so for length 4, you can't really expect any sharp concentration. There are only 4 channels. It's too small, okay? So what I'm going to do is now every time I'm going to increase the size by 2. So I'm going to go from 4 to 8 channels. And what we're hoping for to see a real polarization effect in which some of them will be down here at 10 to the minus whatever. And some of them will be essentially at an error probability of, it should be a half here, I guess. Maybe it's not the error probability. Maybe it's the Bhattacharya parameter. Okay, so let's see how this goes. As the length increases, now I have length 8, things go down, okay? And things become, as you can see, they become, on the one hand, this threshold here becomes sharper and sharper. And so if we go on and on, okay, then this thing will move over and over. And in the limit, if I went to larger and larger lengths, there will be this fraction. So 50% of the fraction of the channel will have an error probability, arbitrarily low, versus 50% of the channels will have an error probability which is, will be useless channels and error probability of a half. Okay, so that's how the actual polarization goes on. Okay, so now let me just try to tell you why these things polarize. Okay, it's actually not very difficult to see, but I'm just going to do the simplest possible case. And the general proof takes maybe 15 more minutes, but it's not much harder. The whole key is to really look at this structure. So this is the structure that is just the basic matrix itself that you have seen, the 1, 0, 1, 1 matrix. And so everything that we need to know essentially happens for this one step, and then all the other steps do simply the same thing repeatedly that I'm going to talk about now. So you have 2 channels, 2 independent channels. You have 2 bits that you input, but you first do this funny transformation with the matrix 1, 0, 1, 1. And you have these 2 observations, right? Now, out of these 2, there will be 2 channels. So what are the 2 channels? Well, the first channel is the one where I'm thinking of this is noise, thinking of this is the input and this is my output here, right? So let's look at this. x1 is equal to u1 plus u2 here, right? So let's write down these equations. So x1 is equal to u1 plus u2. But since it's binary, I can also write u1 is equal to x1 plus x2, okay? I can write down, because x2 is the same thing as u2 here, I can just rewrite this in terms of u1. So u1 is equal to x1 plus x2. And then x1, x2 each go through an independent channel, and I have the observations y1 and y2, okay? So what does this mean? This corresponds exactly to a picture like this. I have two observations, y1, y2, and they correspond to two bits, x1 and x2, and what I'm trying to estimate is exactly the XOR, the binary sum of x1, x2, okay? This is what encoding is simply known as a parity check code, okay? So it's what's called a parity check code. Now, we can do the same thing the other way around. Let's look at the other channel. The other channel is, I know this already, but I want to try to figure out what U2 is, and I have Y1 and Y2. Okay, again, we can write down equations in the same way. So we can write down that U2 is equal to X2. Okay, so U2 is equal to X2, and U2 is also equal to X1 plus U1, and I observe Y1 and Y2. And if you stare at this equation a little bit, you will see that this corresponds to the following scenario, in which I have one bit U2, and I have essentially two independent observations of the same bit, namely Y2, and then I have Y1 plus U1, but U1 is a known quantity. So think of U1 simply as 0, okay? Otherwise, it's just a flip. It's a known flip. So it means you have essentially two independent observations, namely Y2 and Y1, both of the same bit. And you're trying to estimate the bit. And this is what's called a repetition code. And so for both of these codes, what happens now if I want to do the decoding? So think of this as the simplest case is the binary erasure channel with erasure probability epsilon. So a bit is either erased or is not erased. And let's try to figure out how well we can estimate this, given that these things are observed for a binary erasure channel, right? Okay, so these are observed for a binary erasure channel. So the probability that this is erased is epsilon. And the only way that we'll see this non-erased is if both of these things are non-erased, right? Which is 1 minus epsilon squared. Okay, so the probability that it's not erased is 1 minus epsilon. Both of them have to be non-erased, 1 minus epsilon squared, and then 1 minus, that's the probability that's erased, right? And on the other side, it's the same thing. If it's observed with a probability epsilon, the probability that it's not erased, well, if either of them is not erased, then it will be not erased. So I get an epsilon squared, okay? So what happens? I went from two channels that had erasure channels had epsilon here and capacity 1 minus epsilon to two different channels which have these parameters. And it's fairly clear that epsilon squared is, of course, a better channel. It's a much smaller erasure probability. And that this is a worse channel. Okay, so I went from two channels that had behavior epsilon to one which is better and one that's worse. But what's important is that if I'm looking at the total capacity of these two channels, so if I'm adding them up, so what is the capacity of an erasure channel? It's just 1 minus the erasure probability. So the first channel has capacity 1 minus this quantity, which is just 1 minus epsilon squared. The second one has 1 minus this quantity, which is 1 minus epsilon squared. So if you look at the sum of the two, it's just 2 times 1 minus epsilon, which is the capacity of the original channel. So the point is that these are two different channels. One is better, one is worse, but the sum capacity is the same. And this might look very specific to the erasure channel, but this is a general rule. The sum capacity of two channels is the same, but one channel is better and one is worse. And so when I do these things, it's like a stochastic process where things either become better and worse, and it turns out that the only limits that these things can go to is either a perfect channel or a useless channel. Okay, I'm not sure in time.
15 minutes.
Okay, perfect. So now, so this is just a demonstration with numbers. I have two channels, let's say erasure channels with erasure probability 1/2. I put this construction once. I get one channel that is better, okay? One channel that's better is 0.25, has a much better. One channel which is almost everything is erased, 0.75. I do this thing again, okay? Again, now I'll get one channel which is even more useless, okay? Almost everything is erased, but I get one channel which is already pretty good, and I get two channels somehow in between, okay? And so if you do this on and on, then you will see what's important is essentially this distribution of these numbers here, and the claim is that these numbers can only go to 0 or to 1, okay? And so this will be the either completely useless channel or the perfect channels that you have. Okay, so let me just now spend some minutes on trying. So this was for a very specific case, and this is essentially what Erdal proved in his paper in 2007. So he proved that for any binary membrane-less channel, exactly this polarization phenomena would appear if you start with this particular matrix, namely that channels would either become perfect or useless channels. And he also showed that how you can do the decoding, I haven't really talked about this, using this particular structure that looks like an FFT or a fast Hadamard transform. But for doing this computation that you need to do, the calculation of the likelihoods in an efficient manner so that the total number of computations, assuming you can do addition and multiplication in unit time, that this is n log n. Okay? So now the question after that, of course, came, and he proved that these codes achieve capacity for all these channels. Now, he also showed then a little bit later with Emre Teletar how the error probability behaves. And what I mean with this, it's the equivalent of an error exponent result. If you ever seen, let's say, Gallagher's book on error exponent, it shows you that if you're, let's say, transmitting at a particular rate away from capacity, okay, let's say half the capacity or any fraction of capacity, and you're choosing the block length to be longer and longer, as a function of the block length, how does the error probably behave asymptotically? And so we know that from optimum, if you did maximum likelihood decoding and best codes, you could get this error probability behavior to be down exponentially fast. Okay, that's why it's called error exponents. Now, these don't behave quite as good. They behave like 2 to the square root of the block length, 2 to the minus the square root of the block length. So it's not quite exponential. And so one of the first questions was, for example, could you do this maybe even slightly better? It turns out that there's nothing special about this particular matrix 1011. Okay? There are many, many matrices. Essentially, almost any matrix which is not equivalent to an upper triangular matrix does this kind of polarization. And so in particular, you can start, for example, with a 3x3 or 4x4 matrix. And so in general, there's a very easy way then to see how this goes down. It goes down like 2 to the minus n. And then there's something like the exponent of the matrix. And the exponent of the matrix has something to do. You simply look at the matrix, you look at the rows, and you look at the partial distances between these rows. And from that, you can compute an easy number, and that's the exponent. And it turns out that if you're willing to look at slightly larger matrices, you can get this down to be not just like square root of the block length, but essentially any number arbitrarily close to 1, as long as you're willing to take the base matrices to be larger and larger. Okay? Sorry?
Is there an ensemble of matrices that make it easy to compute?
You don't. This is for any specific matrix. So you simply look at the matrix. You look at the top row. You look at the bottom row and look at its weight. You look at the second row and its distance to the subspace spanned by the bottom. You take the sum of these distances, and you take the sum of the log of these distances. That is this exponent. Okay. So then you can look that. If you look at these particular matrices, you can prove by standard classical constructions like BCH, etc., that this measure can go arbitrarily large to 1. Okay? But you pay a price. The base matrix has to be larger. Okay? And I'll come back to this in a second. Okay, so that's nice. One thing that's also nice is you can do exactly the same thing, not just for channel coding, but for source coding. Lossless source coding, that is known how to do once you have optimum codes. Lossy source coding is a little bit trickier. There's a long literature. I'm talking about the simplest possible setup here. Let's say a binary symmetric source, and you want to compress it lossy with a certain distortion. And there's what's called the rate distortion function. It turns out that with these types of codes and a very similar decoding algorithm, you can achieve the rate distortion bound in exactly the same way. And there are many other scenarios, simple versions of the Weiner-Sif and Galford-Pinsker-Prom, simple versions, binary versions of these kind of things you can also do. Now, one thing I haven't talked about is how do you find these good and bad positions? How do you find which of these places are good and bad? Now, Mori and Tanaka showed that in principle you can do this with complexity n log n, assuming that you can do something which is equivalent to convolution of densities in unit time, okay? So there's an issue about, so imagine that you have two densities and you take, let's say, two random variables, okay, and you add them together, and these are independent random variables, then you know that the density is simply the convolution of the densities. So now, if you can do this convolution in unit time, and this is, of course, a matter, how do you actually do this precision? You need to quantize it and so on. But if you can do this with n log n such density convolutions, you can, in principle, determine which are the positions. And it would be interesting to find out now computationally, if you really have quantization, etc., what is the real complexity if you implemented it? You can look at what's called the compound setting, in which you don't maybe know the type of whatever positions you want depend on the channel. And so the question is, what is if you don't know what is the code, what is the channel beforehand? How well can you actually do? And there's some bounds on this kind of thing too. Now, people have looked at non-binary versions, so everything I've talked about binary, but in particular, non-binary is useful for two things. One is if the channel inherently is non-binary. The other one is if you want to have channels where the non-symmetric channels where the input distribution is not the symmetric one. In this case, you can again approach the capacity as long as you know how to do it with non-binary versions. And this group of people showed exactly how to do exactly the same kind of statements for non-binary one. Now, much more recently, Emre and Emmanuel Abe showed how to proceed if you want to, for example, have a multi-axis channel. So now you don't have a point-to-point channel, but you have, let's say, two users and maybe Gaussian noise, so what's called the two-user multiple-axis channel. And it turns out that, again, you can do exactly the same kind of phenomena, but much more interesting even there appears if you look at the two-user multi-axis channel. And again, what happens is that instead of having now, when you do the polarization there, is that you get many multi-axis channels, but they're all of kind of trivial form. So a form where, for example, just one user transmits, the other one doesn't, or the other user transmits, the other one doesn't, it's noiseless, or one where both of them can transmit in a noiseless manner. So they all, again, decompose in a trivial way. You can look at the wiretap channel and look at security issues. There's recently a paper on Bavardi and Madavivar, and I think there's also a paper by Shlomo Shammai, although I haven't actually seen it. And one interesting point is also to look at scaling laws. This shows you the behavior of these codes if you transmit at a fixed channel, at a fixed capacity, and you would like to look at larger and larger lengths. And I told you about this error behavior being 2 to the minus the square root of the block length. But typically, much more important in coding is you fix an error probability, and now what you have as parameter, you have as parameter the channel, the quality, and how close you get to capacity. And you would like to know how these things scale for a fixed error probability, let's say 10 to the minus 10 block error probability. And so this is what you can say with scaling laws. And so this is exactly now maybe the only, let's say, question mark for polar codes, but it's unfortunately a somewhat big question marks. It turns out if you're looking at the behavior here, that these polar codes, and this, you can also see this in practice, what they are not good at is that you need to have very large block lengths. Okay? So it turns out that, for example, if you want to transmit at a fraction delta of a fraction 1 minus delta of capacity, so let's assume you want to transmit at 99% of capacity, so delta is 0.01, then, and you want to achieve a certain fixed probability of error, how large does the code have to be? Well, it turns out that the scaling is it has to be delta, or 1 over delta, to the roughly 4th power. Okay, so let's assume you want to transmit only have 1% away from capacity, then it's 10 to the minus 2 to the 4th power. Okay, so things scale like with the 4th power. So as you approach capacity, unfortunately, the block length has to be very large. How does this compare to classical coding? Like for things like iterative codes, we don't have exact statements, but people assume that it scales like 1 over delta to the squared power. Okay, so it means the block length is much, much shorter. So that brings me also to the summary. I hope I have conveyed that this is something very elegant, something very close to the original spirit of Shannon, something that bridges information theory, encoding, is a completely new perspective on codes. Now the question is, if you go out now and next time buy your cell phone, will be there polar code in your cell phone? I guess I don't know. Okay, I will probably have to wait another 2 years to see whether or not people can somehow change the scheme to make it work for reasonable block lengths, 1,000, 10,000, and make it competitive. If that's possible, then I think these are, due to their nice structure, elegance, etc., are very good candidates for future products. And maybe the next company that Meyer founds, will be in there. Okay, but if not, then perhaps it will be something still very nice, something elegant, something people that probably will use in papers, but perhaps it will turn out not to be a new groundbreaking technology. Okay, thank you very much. That's it. Not found a combination of, let's say, two or more that would do something better. Okay, it's very hard. For example, for 2 by 2, this is the only polarizing matrix, and it takes up to, I think, a 10 by 10 matrix to beat that exponent. So, and even combinations, we have not found ways to make it better. Okay? And if you go for a 10 by 10 matrix, you need maybe about 20, 30 steps for the polarization to take effect. You start something with 10 by 10. Every time the block length goes up by a factor of 10, right? So 10 to the 30.
That's quite.
Yeah.
What about the decoding complexity? How does it trade off?
It's n log n. So that's quite nice. Even if you look at the even if you look at the complexity as a function of gap to capacity, that's probably one of the best schemes that we know. But you need large. So complexity is not an issue, but you need very large block.
A question about the selection of the rows that you're using in generative matrix. You mentioned the rule by Rüdiger that you need to choose the rows with the highest Hamming weight. So how is this rule different or similar?
We think that if you look at very large matrices, we think that it might even be almost exactly the same in the sense that if you look at the intersection of this thing, then I don't know. A student of mine thinks that actually in the limit, the size of the intersection actually goes to 1. But it still doesn't mean you can just use Rüdiger codes, because in the successive one, if even a single channel in between is not good, then you are out of luck. Okay, you need to make sure that all of them are good. So there's a little bit an issue. But the conjecture is that Rüdiger codes are very good, and certainly under optimal decoding should also achieve capacity. But I don't know if it's proof of this.
When N is feeding, then even if the channel for one of the bits is so-called P, you will still have some error phenomenon, and then the error will propagate to
right. So I only showed these small little examples. You will never use this for length 8. Okay. Now the point is, since the error probability goes down so quickly, just by the union bound, okay, you simply multiply by the length of the code, and that gives you an upper bound on this error propagation. Okay. So, but since the error probability goes down like 2 to the minus square root of n, this extra factor n in front doesn't make any difference. But that's also one of the reasons it has to be still reasonably large, because asymptotically it doesn't make a difference. But for length 1,000, it still doesn't make a difference. Okay.